Hey everybody, my name is Alex Feldman, and it's a great honor for me to host Rob Holte from University of Alberta, Canada. He is a professor emeritus. So Rob Holte, Professor Holte, studied computer science in University of Manitoba, computer science in the same university for a Master's of Science, and then he did a PhD at Brunel University in England. And he has a fantastic number of articles and contributions in various AI disciplines such as machine learning, heuristic search. Actually, heuristic search is a big thing in his career. Game theory. One of my favorite contributions of Professor Holte is in helping solve a small poker game. Hopefully he's going to talk about something else tonight, but hopefully he can come another time and talk about both game theory and machine learning and search and AI in general. He has multiple honors and awards. An impressive one is the Outstanding Paper Award at the Association for Advancement of Artificial Intelligence. He has many appointments, PhD students, and actually he has written so many papers that I was saying today that he's becoming like the Erdos of artificial intelligence. If you co-author a paper with him, you get like a Holte number, and I hope that I'm going to get like number 1 or 0. I don't know how the counting is done. But just before we start, one thing, please hold your questions for the end of the talk because of the format of the presentation and the streaming, live streaming and everything. There is going to be time for questions and answers at the end of the sessions. Well, so thanks.
Thank you. No, thank you, Alex, for that gushing introduction. There's definitely lots of exaggeration there. Don't believe everything you heard literally. It's an exciting time for artificial intelligence. As probably you all know here in the audience, it has, of course, as a discipline, has been around for 60 years, but at this point in time, more than ever, there's a huge movement of ideas out of the academic research labs and into the industrial context. And so that's what's generating a lot of the excitement. But it's also what caused me to choose this particular topic to talk about today, because I think that there's a risk in moving things from the academic setting into the industrial setting that maybe lots of people aren't aware of. And so that's really what I'm talking about today. There will be a technical part to the talk, but the important part of the talk is the first 10 minutes where I tell you what that risk is. And it comes down to, so a classifier is, just use your imagination. I'll have a little slide on what a classifier is, but it's the cost-sensitive part to this that is one of the key differences between doing work in the academic setting and doing work in the industrial setting. And so imagine you've got a classifier. It's categorizing things as positive or negative, and it makes a mistake. Well, if you're in the academic setting, what does this mean? It's a number in a paper that you've published, and you've got this many mistakes by your classifier. It has no real consequences. Assuming the paper isn't rejected because you have such a large number of mistakes, then it has no real consequences, just a number. But in a real world, if your classifier is actually being used for something, then a mistake can be extremely costly. It could cost your company millions of dollars. It could even cost a life. And so the impact or the importance of measuring classifiers, evaluating classifiers, and really paying serious attention to their costs, and not just counting the number of mistakes, is the big difference between the way academics have traditionally evaluated their classifiers and what I'm going to talk about today, which puts huge emphasis on the costs of misclassification. So this is work I did quite some time ago, but I think that because of the interest that I just mentioned, that it's worth repeating. This is work that I did with a former PhD student, Chris Drummond, who's now at the National Research Council in Ottawa. But just before I get into all the exciting stuff, I just want to let you know where Edmonton is, in case you're not aware. You guys are on the map here in the bottom left, and Canada's the green bit at the top there, and the province of Alberta is colored in yellow. And if you look at the smaller version of Alberta there, then you see there's 2 black dots. The one in the south is Calgary, and the one in the middle of the province is Edmonton. So that's where I come from, and it may look like it's far away and near the North Pole and stuff like that, but it's actually only a 3-hour flight from SFO. So if you want to come visit, then you don't have to worry about a lengthy trip. It's a direct flight. It turns out that, I mean, obviously you guys are here in Silicon Valley and there's tons of excitement about AI and so on. There's tons of excitement about AI in Edmonton too, and that probably doesn't make the newspapers here, but we're pretty happy what's going on there. According to this one ranking system called CS Rankings, which has a certain amount of credibility, by the way. I know there's lots of ranking systems out there, but it actually shocked me to discover that my computer science department ranks 3rd in the world when you just focus in on artificial intelligence and machine learning. And so that shows you that we have a large number of very high quality AI researchers. And the two main areas that I would say are our specialty. We cover a broad range of artificial intelligence topics, but the two specialties are reinforcement learning, where you might know the name Rich Sutton. He's the founder of that area, the founding father of reinforcement learning, and it's a style of learning that I think is, you were asking me what's the next great thing. One of the next great things I think will be reinforcement learning, and so we're kind of leading that charge there. And the other one that we have is computational game theory, which I have not been too much involved in myself, but our poker research group was the first to beat human, real human professionals at the Texas Hold'em no limit game, and we actually completely solved the Texas Hold'em limit game, and so we have some pretty good credentials there. About a year and a half ago, the Canadian government launched what they call the Pan-Canadian AI strategy, and they chose just 3 centers in all of Canada to be the hubs for artificial intelligence. Montreal was one, Toronto was the second, and Edmonton was the third. So we're doing pretty well. We're recognized by the Canadian government for our strength. And you might also know that the first DeepMind lab after the initial one in London actually was set up in Edmonton with Rich Sutton and Mike Bowling from the Poker Project as the scientific leads. There's lots of other things I could say, but this talk isn't about Edmonton. I just wanted to let you know that we're not on your radar, but maybe we should be. And if anybody's interested in knowing more about what's going on, or if you think you might want to come up and visit, then just contact me. And if you don't have my email address, I can't remember if it's in the information, then Alex or other people here would have it. Okay, back to the technical part of the talk. I just wanted to take a couple of minutes out there to let you know where I'm coming from. So classifier, I used the word in the title. I didn't define it, but it means, in this talk, it means what it means in ordinary language. It's a system that assigns an object to one of a fixed set of predefined classes. And so, a good example is a metal detector, like you might see in an airport. And so there's the metal detector, and when you walk through it, it puts you into one of 2 categories. You're either in the sound the alarm category, or you're in the green light, have a nice day category. Okay, and so it's putting you, they have these 2 predefined classes. There's nothing in between. There's not like a histogram bar that says he's 50% good and 50% bad or anything. It's predefined classes. When you only have 2 classes, and that's what I'm going to focus on in this talk, when you only have 2 classes, it's called a binary classifier. And I'm going to use generic names, positive and negative, for those 2 classes. So that's what a binary classifier is. There's another kind of classifier which ultimately is a binary classifier, but it's built on top of a different kind of system. So there are some systems which, instead of putting you directly into a category, they produce a score. So there are examples like neural networks where you have an output neuron, and the output neuron is, let's say, a number between 0 and 1. Or you might have a probabilistic network, like a Bayesian network, where, again, the output is between 0 and 1, but it is supposed to represent a probability. So those systems are not classifiers. They are giving a numerical score and not putting you into a category, but there's an obvious way to turn them into binary classifiers, and that's to use a threshold. So you threshold their score, and then for any particular setting of the threshold, that combined system is a binary classifier. And I'm going to use the convention that if the example has a score that's bigger than the threshold, it's positive. So that means for every different setting of the threshold, even though the underlying system hasn't changed, you have a different binary classifier. And these are very common. There, I just said that. Okay, so binary classifiers are nice and simple to think about when you think about what kind of mistakes can they make, because there's only two kinds of mistakes. And the two types of mistakes are called false positive and false negatives. And so a false positive in this setting is where the alarm sounds, but the person, which in this case is just a skeleton, is not carrying any metal. Okay, so that's a false positive. And then, of course, the false negative is the other kind of error where the alarm does not sound, but the person is carrying metal, or in this little example, is made of metal. Okay, so those are the two types of errors, false positive and false negative. Now, how are we going to evaluate a classifier? And there are actually different approaches to evaluating a classifier. And one of them would be that you, as a human being, maybe even as a human expert, you inspect the classifier and you look at it and you say, that makes sense, that's probably right, et cetera, et cetera, et cetera. But we're going to do what you might call empirical evaluation, where you have a big data set, where you know for each one of those examples in that data set, you actually know the true class. You know what it should, how it should be classified. And so that's called the test set. And so this is a very, very common way of evaluating a classifier, is to take a test set where the true class is known, and then you run those examples through your classifier, and this is going to be how you figure out whether it's, how good it is. Okay, and so if you think about it, the rows there are defined by the true class of the examples in your test set, and then the columns are defined by the output that your binary classifier made. And so there are the four options, as you can see. There you could, the correct answer could be positive, and your classifier said that the example was positive, so that's good news. Both of the green boxes here are good news because it's truly positive, truly negative, and your classifier said it was negative. Those are called the true negatives. And then you can see in the other areas, you've got the false negatives in the top right of this matrix, and you've got the false positives in the bottom left of those matrices, and those are the errors. So that is what's called a confusion matrix, and that is going to be the fundamental building block that we're going to use for evaluating classifiers. I've put a hash symbol in front of these because when the raw output from this evaluation is a count. How many true positives, what number? It might be a number like 75 or something like that, but the first thing that almost everybody does is to reduce these things to percentages. So instead, if you had 100 test data that truly were positive and your number of TPs was 75, instead of using the number 75, you'd use 75%. And that's called the true positive rate. So we're going to use these rates, which is just a number divided by the total, okay, by the row total. So the false negative rate is the false negative number divided by the total number in the top row, and the false positive rate is the number FP divided by the total number in the bottom row there. So those are the two rates that we're going to talk about in this lecture. And those, again, are the funding. This is now starting to build up to the way we're going to evaluate classifiers. Now, I already said on my opening slide that the one big difference between the real world and the academic world was the impact that an error has. But there's other differences, and that's what this slide is about. And the first thing I want to talk about is when you're evaluating classifiers, okay, we've got this input, the true positive rate and the false positive rate, but we want to take some other factors into account. And the two factors that I want to take into account in evaluating the classifier, I'm going to call the class distribution and the misclassification costs. So we have positive and we have negative examples, and what is the probability, or what is the percentage, what's the probability that the classifier will be given an example from the positive class when it is actually used? Okay, this is different than what the probability is in the test set. Okay, the test set might be 50-50 positive and negative, but it might be that when you take that classifier and put it in the real world, that the probability of a positive example is only 10%, or only 1%. And so I call that the deployment situation. It's the situation where the classifier is deployed, and those are the factors that you need to take into account if you are thinking about deploying this classifier in that situation. then you want to know how will it perform in that situation, not how did it perform in the lab. And this is a fundamental distinction that, of course, if you're only working in the lab, you don't think about this. But as soon as you want to take something out of the lab and put it in the real world, you have to worry about factors in the deployment situation. And one of them is the class distribution. It makes a huge difference to the performance of your classifier. The other thing you have to take into account are the misclassification costs. And there will be two of those, because there's the classic misclassification, the false positive and the false negative each have a cost, and they're often very different. So in the example that I had of a metal detector, it might, what do you think about somebody who has not got metal and you signal the alarm, what's the cost? It's a bit inconvenient to them, and maybe you have to hire a few extra security people to do extra checks on those people, but it's not the end of the world. Whereas if you make the other kind of error and you let all sorts of people through with metal onto the airplane, then that's not good news. Typically, something bad could happen there. And so there's a high cost to that kind of error. So you can see how there could be, the two kinds of errors could have vastly different costs. Again, you could think, well, if you're in the lab, you could make up some numbers for these costs, but what really matters is what is the cost in the specific deployment situation where this classifier is going to be used. So that's those are the extra costs, the extra factors that I want to take into account in evaluating the classifier. Of course, the numbers we got out of the confusion matrix tells you nothing about these things. These are independent variables, if you want to call them that. And the thing that's worse, and this is where it gets really tricky, and this is why I was able to publish a paper about this, is because these are not known. Okay, so it almost sounds like an impossible thing. You want to evaluate the classifier, taking into account factors that you do not know. Okay, because you don't know necessarily you're building this classifier, and maybe you're going to sell it to 100 clients, but you haven't identified those clients yet, and some new client walks in, and you don't know what their deployment conditions are. And so it sounds like it's an impossible thing to do, but I'm going to show you that we have at least one technique that Chris Drummond and I developed, where you can do a very good job of evaluating classifiers without knowing these factors. You can take them into account without knowing their exact values, or even knowing really hardly anything about them. And this is important because in many applications, these factors actually vary with time. And maybe the deployment is relocated. Maybe the classifier starts off here, but the company decides to relocate. It takes the classifier with it, and now suddenly it's 10 miles down the road or in a different state or something. And so it's an important thing to do. These are really important factors, and you want to be able to cope with them as best you can without actually knowing anything about them. Like I said, it sounds impossible, but you'll see that it's not impossible. The final point I want to make, and this is a bit of a soapbox that I always get on, and I don't know if there's too many machine learning people in the audience, but it's very common in the academic world that remember we have two numbers coming out of our confusion matrix, the false positive rate and the true positive rate, or the false negative rate is the equivalent. And it's very common in the academic world to reduce this to a single number. And so sometimes you get people reporting the accuracy of their classifier, sometimes you get people reporting the expected cost of their classifier under a variety of conditions. You might get them reporting, a very common one these days is the area under the ROC curve, and so on and so on and so on. So this is taking two numbers that are fundamentally independent of each other and reporting or squeezing them into a single number. And hopefully it's clear that important information is being lost. And I'll illustrate that in the next couple of slides. So if you're not going to squeeze them down to a single number, what is the alternative? And the alternative is to visualize them as a pair. We've got a pair of numbers, so let's take a pair of numbers and do some kind of visualization and keep both of them alive, and keep both of them separate. And so the two forms the traditional way of doing this, and it's quite common, although the machine learning people haven't seemed to have really seen the value of the visualization techniques, is the ROC curve. It's pretty common in the medical world. It's been around since the war, World War II. And then I really fell in love with cost curves. I thought they were the greatest things since sliced bread. And then when I first tried using them, I realized that they had problems. And so Chris Drummond and I were trying to write a paper using them, and it just didn't work. They just didn't work for us. And so we invented on the spot these cost curves, and they really worked much better for us. So how many people in the audience actually know what an ROC curve is? Okay, and how many don't? Okay, okay, don't panic. Okay, so you don't have to know what an ROC curve is to understand this talk at all. I'm talking at a rather high level. Even when I get into the technicalities, everything's pretty simple. But I asked that question because I will make reference throughout the talk to ROC curves, because typically an audience is exactly like this. It's mixed, and I want the ROC people to know why they should switch over to cost curves. And for those of you who don't know what they are, you should read about them. They're actually pretty nice. I'll show a bit of them here. The only thing I want to mention about single numbers, one of the things that's attractive about them when academics are writing papers is that they take up a small amount of space. But the real advantages of them from an intellectual point of view is that we know how to average numbers. You all know how to average a number. Some of us know how to compute confidence intervals and tests for significance and so on. And these are all things that are routinely done in machine learning and classifier evaluation generally. And so that's the point. The other 2 points on this slide I'm going to skim over, but that's the point that I want to emphasize is ideally we would not lose these things. These important, powerful things that we do with numbers, we would not lose them when we moved over to curves. And it really is the unfortunate thing about ROC curves is we don't even know how to average them. And so they're just off to a very bad start. Whereas cost curves, we will be able to do all of these things that we can do with numbers. So ROC space, here we go. I'm going to now give you the world's shortest introduction to ROC curves, but in fact they are very simple. Remember we had these two numbers coming out of the confusion matrix, the false positive rate, and I called it earlier the false negative rate, but if you take 1 minus the false negative rate, it's the true positive rate. And an ROC curve just says, well, these are two independent numbers. Let's make a two-dimensional plot. And we'll have false positive rate on the x-axis and the true positive rate on the y-axis. And if you give me a binary classifier, it has a false positive rate and a true positive rate, and we'll just put our finger right there on the space, and that'll be it. So the perfect place to be is in the top left-hand corner, because that has a false positive rate of 0, which means it's making no mistakes on the negative class. It has a true positive rate of 1, which means it's making no mistakes on the positive class. So it's not making any mistakes at all. So that's the perfect classifier. As I said, if you've got a binary classifier, as shown in green here, it has a false positive rate. That's its position on the x-axis. It has a true positive rate. That's its position on the y-axis. And you just put a dot there and then join it to the two corners of the ROC space, and you're done. And that's the ROC curve for a single binary classifier. If you have a threshold-based classifier, then as I mentioned when I introduced them, for every setting of the threshold, you get a binary classifier. And what that means is for every setting of the threshold, you get a point in ROC space, and you join them somehow to make a beautiful curve, convex curve, that again goes from 0, 0 up to 1, 1. So that would be the ROC curve for a threshold-based classifier. And so that's what they look like. They're a very simple concept, and they do keep the two numbers separate. You're losing no information from these things. You can obviously read it off by looking at the x and y axes. Oh yeah, AUC. So the area under the ROC curve is exactly what it says it is you can look at these curves and you can compute the area underneath them. And obviously with one, you saw where the perfect classifier was. It has an area of 1.0. And so the bigger the area, the better you are in general. The in general part's an important caveat there. As you can see in this case, the area underneath the green curve is smaller than you can see it visually, is smaller than the area underneath the blue curve. And so you would prefer the blue curve to the green curve if area was the way you were measuring performance. But is it always the case that a bigger area under the curve means you have a better classifier? And the answer, and this is me coming back to the point I made earlier about reducing things to a single number. So we've taken those curves that have both numbers in them and reduced them to a single number. So here's a couple. There's the red curve and the black curve. And the red curve, you don't have to do the math. There it is. It has an area under the curve of 0.95, almost perfect, because the perfect area is 1. And you have the poor black guy over there whose area under the curve is 0.6. is very low, because if you just draw a diagonal line from 0, 0 to 1, 1, you have an area of 5, and you can achieve that by making completely random guesses. So an area under the curve of 0.5 is random. An area under 0.6 is just barely better than that. And so people who routinely use area under the curve to choose between classifiers would not have any doubt about which classifier to use. They would choose the red one and throw the black one away. It's not the right action. Because when the positives outnumber the negatives by a ratio of 16 to 1, then the red classifier, the one we thought was the good one, has twice the error rate of the black one. Even though its area under the curve is so much better, in this particular deployment setting, if this was the deployment setting, you'd be nuts to use the red one. The black one is so much superior that you'd really want the black one. And so this is an example where the problem fundamentally comes from the fact that you've taken the two numbers and shrunk them down to 1. And for any of you who've worked with real data, a ratio of 16 to 1 between the two classes is actually not a severe imbalance. There are many situations where you have 100 to 1 or 1,000 to 1 ratio between one class and the other class. And so in that case, of course, the black would have, again, the same kind of error rate. It would be 100 times better. The red classifier would have 100 times larger error rate than the black one. And so, so this is just an example where those single numbers can really completely mislead you. And so the advantages of visualization, this is ROC curves again. We have curve A, the blue one, and curve B, the red one. The advantages of visualization typically are if you see the lines cross, what it means that under some circumstances, you should use one of the classifiers, and under other circumstances, you should use the other classifier. It means no one classifier is the better for all situations. So you have to choose between them based on those factors I talked about. You cannot just choose the blue one or the red one and be doing the best you could do under all circumstances, given that you have the choice between these two. One of the weirdo little technicalities for the people who like ROC curves is, so here we see ROC curves that are crossing. And they tell you what I just said. They tell you that you should use A sometimes, and you would prefer to use B sometimes, some other times. But what's interesting is that crossing point does not tell you when you should use A and when you should use B. It just tells you that such conditions exist, and you need to then use some other jiggery-pokery to figure out when you should use A and when you should use B, and it's not visual at all. So, but this is the final point, the final place where I want to make a really important point, is when you have everything reduced to a single number, what kind of question can you ask? The only kind of question can you ask is my number bigger than your number, right? If you have to ask the question that way because the numbers are all in a line, they're totally ordered. All you can ask is my number bigger than your number? And so all the questions that you ever see asked by people who reduce performance information to single numbers are what I call is questions. But we see now that that isn't the right question at all. Like, it's not even the right question. Never mind, can you get the right answer? It's not even the right question, because the only question that makes sense in a setting like this is a when question. When is A better than B? Not is A better than B. It doesn't even make sense to ask that question. The only question that makes sense is when is A better than B? And these visualization techniques ideally would, first of all, they make the fact that the answer is not always pop out at you because you can see the crossing lines. And then ideally, a visualization technique would directly allow you to see the answer to the when question. And we'll see that cost curves do that. And so now I'm going to introduce cost curves. But I'm going to introduce a simplified version of them. Remember, there's these two factors that we want to take into account, the misclassification costs and the probability of a positive example in the deployment situation. So the one that's easy to think about is the probability of a positive example in the deployment situation, which I call P+. So there it is on the x-axis there, and it's a probability, so it ranges all the way from 0 to 1. Now, the reality is that 0 is not probably a realistic scenario. You know, the probability of seeing a positive example being 0 is not one you're likely to run into in your everyday application. And the same thing can be said for the extreme right-hand side. But they're there, they serve a useful purpose that I'll illustrate in a second. And so that is the x-axis, and the y-axis is error rate. So what's really natural about cost curves is that what you have is a performance measure as a function of an unknown. It's what really all plots should be. Your unknown is x, and the thing that depends on it, the dependent variable, in this case the performance measure, is the y-axis. It's like the classic reason you draw these kind of graphs is because you have a dependent variable and an independent one. Okay, so we got p plus on the x-axis and error rate. How do we draw a cost curve, or what is a cost curve in this slightly simplified setting? Well, let's have a look at the blue classifier here. He's got a false negative rate of 0.6 and a false positive rate of 0.3. And let's think about what would be the overall error rate. Like, these are the error rates on the individual classes, but what would be the overall error rate of this classifier in this extreme world? There are no positive examples in the deployment situation. In that strange, extreme, exotic world, what is the overall classification error rate of this classifier? Can anybody give a guess? 0.3 is the false positive rate, and there's no positives, so all we have is negatives. Now, false positive rate is the error rate on the negatives, and all we have is negatives. So the answer is that the error rate, overall error rate of that classifier is the false positive rate when x is equal to 0, when p plus is equal to 0. And in many ways, that's why we include that x equals 0 on the graph, is so that we can easily identify the height of the cost curve when x is equal to 0 or p plus is equal to 0. What about the other extreme? When you're in a world where there's nothing but positive examples, x is equal to 1.0, then you're probably already on top of that, because you guys are, it's a smart audience, is you recognize that the overall error rate is the false negative rate in that extreme world there. And then the other thing that you can figure out with just by looking at the formula for error rate is that error rate is a linear function of p plus, and that's the cost curve. The cost curve just shows you the error rate for all possible deployment situations. All possible deployment situations, here we just have p plus, is recognized, is represented by the x-axis, and then the performance in all possible ones is represented by this straight line. False positive height at x equals 0, false negative rate at p plus equals 1. And so that's cost curves, and you almost know everything you need. You basically need to know everything you need to know about cost curves. They look like this for binary classifiers. The classifier, just to get a little more practice in here, it's like being back in school again. Here's the green classifier, or second question on the exam. Draw the cost curve for classifier number 2. We'll go a little quicker here. There it is. But it's drawn in the same way. You just put your fingers here and there and draw a straight line between them. By the way, again, just for the mathematically inclined, there's an intimate mathematical relationship between ROC curves and cost curves. It's called a point-line duality. And what it means is that every point in one of the spaces is a line or line segment in the other space. And so remember in ROC space, we took when we had a classifier, it ended up looking like a point in ROC space. And that point gets translated into this line in cost curve space. So point-line dualities are handy things to know. You can go back and forth between the two spaces with simple mathematical transformation. So there's the green classifier, and just for some illustrative purposes, we have a third classifier here, the red classifier, and it looks like this. Okay, so what can we tell? Again, remember, these deployment situation, we don't know anything about these factors, but what we can already say about these classifiers. Which ones should we use and when should we use them? Well, let's look at the red one versus the blue one first of all. If you look across the whole spectrum of deployment situations, what you'll see is that the error rate of the red classifier is always below the error rate of the blue classifier. There is no situation in which you would prefer the blue classifier to the red classifier. And so the blue classifier, you throw it out. Don't even pay a penny for it. You will never use it if you've got this choice of these three classifiers. So then, do I have that on the next slide or no? Okay. So the red one's gone. What about the blue one, or sorry, yeah, the green one versus the red one? Well, you can all see that they cross. And as I mentioned earlier, when you see performance measures like performance curves like this cross, it means under some circumstances you would prefer to use the red classifier, and under other circumstances you would prefer to use the green classifier. The nice thing about cost curves compared to ROC curves is that you can see exactly what deployment situation you would change over. And it's where they cross. It's where the two lines cross. You know, what X value is that? I mean, I never can see it right from where I'm standing, but it's about 0.77. So when you have a P plus of 0.77, you should switch over from the red one to the green one in order to minimize your error rate. So what this is telling you is that you don't have to know the deployment situation's P plus exactly. All you have to know is it bigger than 0.77 or less than 0.77? So it becomes more of a hypothesis test rather than an actual careful measurement where you need high precision. You don't need much precision at all in order to decide between them. And if you're very close to 0.77, as we'll see later in the talk when we talk about significance testing, then it probably doesn't matter which one you use anyway. On the next slide, we're going to see a reason why you would actually never use the green classifier either. So, but on this slide, given what I'm showing you, to introduce the idea, the blue classifier is dominated by the red one. The green one and the red one cross, and so under some circumstances, you'd consider using one, and on the other circumstances, you'd consider using the other. But there is a reason that I'm showing you now why you would actually never use the green one. And that's because, in addition to these two classifiers, there's two classifiers that you always have available to you. You don't have to pay anything for these classifiers. They're free of charge. And that is the classifiers that always classify things the same way. No, they don't even look at the object. They just say, one of them says, this is positive. Always, always, always it says, this is positive, without looking at the object. It's like going into a doctor's office and he says to every patient, you're healthy. Okay, so go away. It's a very quick way to be a doctor. You probably lose your license, but so that's what I call the trivial classifiers. One trivial classifier says everything is positive, and the other one says everything is negative. These are classifiers. They have true positive rates and false positive rates, and they look like that. The one is on the main diagonal, and the other is on the back diagonal. And so these are classifiers you always have. And so now you ask yourself, under what conditions would you use the green classifier? And we already talked about you would only use it compared to the red classifier if P plus was greater than 0.77. But you can see that once P plus gets to be greater than about 0.7, the green classifier and the red classifier are both worse than one of the trivial classifiers, the always positive classifier. So once P plus is greater than 0.7, you would not use either of them. Okay, so that eliminates that section for the green classifier, and anything less than 0.7, the red classifier dominates the green classifier. And so the green classifier is not dominated by any single classifier alternative, but it's dominated by collectively by the alternatives. So out goes the green classifier. And so we have this concept of the operating range of a classifier, which is what is the smallest and largest P plus values where it's better than both of the trivial classifiers. And so the red classifier has that operating range. If you computed the green classifier's operating range, it would be a subset of the red one, and inside that subset, it would be always worse than the red one. And so that's another way of saying what I just said. So that's the concept of operating range. And again, it's very visual. You can just read it off a graph that has the trivial classifiers plotted on it. This leads naturally to the idea of a lower envelope, where for each section of the x-axis, you draw the lowest classifier. And this isn't a very exciting one, but you'll see some of these in other plots I'm going to show you later on, where you compute the lower envelope. Again, for ROC people, they often take the convex hull of the points in ROC space, and the ROC convex hull is the point line dual of the lower envelope in cost curve space. All that was with binary classifiers, but I know you're dying to know what cost curves look like for when you have a varying threshold classifier. Remember, they were these nice, beautiful, sweeping convex curves that we saw in ROC space. They don't look quite so, depends on your aesthetic, actually, whether they're more beautiful or less beautiful in cost curve space. So imagine that we set the threshold to infinity. So what's going to happen? Every example is going to be classified as negative. So the always negative line is actually the cost curve when the threshold is equal to infinity. And as you lower the threshold, you'll start to get some numbers, some examples that are classified as positive, and so you'll move down here, you'll move down, and so on. And eventually, when you make the threshold equal to minus infinity, you'll be classifying everything as positive. So this is what the cost curve, it's not really a curve, it's a collection of curves, looks like for a varying threshold classifier. And so the bad news is it looks like a jumble of lines. Well, it is a jumble of lines. So it isn't the beautiful points that you see in ROC space. But for me, the thing I like about it, especially being a guy from the 60s who grew up with string art, is that the lower envelope jumps out. It just jumps out at you. You cannot miss seeing the lower envelope here. And that's the important part of the whole plot, is the lower envelope. And you can see instantly that no setting of the threshold will get you an error rate less than 0.3. So if you don't like that, then you have to start from scratch again. That's the best you can do here. Oh, maybe there's a point as you get over to the right-hand side. Sorry, I'm looking at the 50-50 line there. So some aspects of this jump out straight away, and other aspects don't. But I think the lower envelope is an important thing to have jump out at you. So I started, to introduce these. I said I'm going to simplify, and I'm only going to take one factor into account. I'm going to take P plus into account, the probability of seeing a positive example in the deployment situation. But now I'm going to show you how we're going to take misclassification costs into account. And the first thing we're going to do, and this is really the key mathematical trick, is we're going to fix the relationship between y and x. So it's still going to be a plot. There's going to be y is some kind of performance measure on the y-axis, and x-axis is going to be something that takes into account P plus and the two misclassification costs, all on one axis. But we're going to hold the relationship is y is going to be the false negative rate times x, whatever x is, like we're going to redefine it, plus the false positive rate times 1 minus x. So that's going to be our little trick, and I'll explain why it's a trick in a minute or two. But up to this point, what we've done is we've said, okay, we're going to let x be P plus, and if we plug P plus into that formula, we get the formula for error rate. So when I showed you these pictures earlier, and I had error rate on the y-axis, it was not an arbitrary choice. It was chosen because I had this relationship between y and x in mind, and so as soon as I pick a definition for x, I get a performance measure. Whether it's the one I want or not, that's my problem. But I get a performance measure because y is intrinsically related to x by this formula, the way Chris Drummond and I approached all this. Okay, so what are we going to do to take costs into account? We're going to make up a new definition of x. And it looks complicated, and there's actually a couple of different ways of motivating this. I'm not going to tell you any of them. Okay, so that might be a good, let's not even leave it for question period. Anyway, it turns out that you can see in here, if you look close enough, there's P plus. This is the cost of misclassifying a positive as a negative. Somewhere over there, there's the cost of misclassifying a negative as a positive. It takes all three factors into account in this funny looking formula. And if you define x this way and keep that invariant relationship between y and x, then y is expected cost, normalized to be between 0 and 1 because our y-axis goes from 0 to 1. But in fact, one way to motivate that definition of x is because that's what you want y to be. If you want y to be expected cost normalized to be between 0 and 1, and you work backwards through that formula, you get this definition of x. It's actually not the way we came up with it, but it's one of the 3 or 4 ways of understanding what that x formula means. So it looks complicated and looks messy, but it does the trick. It does what we want to do. It takes all the deployment factors into account and comes up with expected cost, normalized expected cost on the y-axis. So it does exactly what we want to do. So you might wonder what is the next few slides, as I'm going to show you all the stuff I just showed you all over again, but I'm not. Because the beauty of using that invariant trick, where y is an invariant relationship between x, means that everything I just told you when x was defined as p plus is exactly true when x has got this definition. In fact, it's true whenever x has any definition, because y is a linear function of x, if you look at those formulas. And when x is equal to 0, it's the false positive rate, and when x is equal to 1, it's the false negative rate, et cetera, et cetera. It's a straight line relationship, so everything I just showed you is still true. Cost curves, even with this, taking all these factors into account, are still straight lines joining fp at one end and fn at the other end. And they cross, they have operating ranges, everything is exactly as I just told you. So you now know everything about cost curves, the basic cost curves, and how to draw them and what they mean. Okay, but I now want to take a moment to compare ROC curves to cost curves. And hopefully this will be meaningful to everybody here. So this is actually work that was done by one of the guys in our department, Russ Greiner, in concert with the Cancer Institute in Edmonton and the doctors there. There's these three standard tests for a condition that I can hardly pronounce, medical condition, but there it is up there at the top. And this is ROC space, and so they have certain false positive rates and false negative rates. And then you see the black curve, or the red jagged curve there, is a new classifier that Russ Greiner and these colleagues came up with. And they were trying to publish a paper arguing that their classifier was much, much better at detecting this condition than the existing techniques. But if you look at the ROC curve, that conclusion does not jump out at you. And this is, in fact, the same problem that I had with Chris Drummond way back when we were working on a completely different problem. But we had the same issue with ROC curves, is we were sure in our hearts that our technique was superior, but it didn't show up in the ROC curves. And if you look, I just zoomed in now on the ROC curve. It's exactly the same one as before, and you can see, look how close, the existing ones are to that black one. Like if you're looking at the ROC curve, it doesn't look like there's any difference. And yet, if you look at the cost curve, you get a completely different picture. And this is the correct picture to be looking at here. Is you can see that first of all, the existing ones are barely better. The dotted lines here are the trivial classifiers. The existing ones are barely better than the trivial classifiers. And so you wonder why you use them at all. And then you look at the black line, and it can get way down there to a very good, depending on exactly where you are in the curve. It has a broad operating range, and you can get very good classification compared to the existing techniques. And so when you look at this curve, you know you should be buying their classifier and not using the standard ones. And so it's like night and day. And it's funny because there's this point line duality, so they're showing you the same information, and it's just how is the information being presented? And this is just a more effective way of presenting the information. I talked about things that we do with numbers that we like to do, that we would like to do with these curves, and I'm going to go quickly through that, and that'll be the end of the talk. So averaging is important. It's very important to machine learning people, and maybe not everybody in the room is a machine learning person, but typically when you evaluate a classifier that's created by a machine learning system, you use a technique called cross-validation, so n-fold cross-validation. And what you have to do there, this would be an example, hypothetical example of two-fold cross-validation, where you take half the data, use it to train, to create a classifier using machine learning, and then use the other half of the data to test it, and that creates a cost curve. And then you flip the roles around. You take the first half of the data and use it for testing, and the second half of the data and use it for training, and that gets you another cost curve. And now you want to combine those two things. This is how cross-validation works. You then combine those two results by averaging them. Well, if you can't average curves, then you can't run cross-validation, and you're kind of hooped in terms of standard machine learning methodology. But these curves, because you have the independent variable on the x-axis and the dependent variable on the y-axis, you just average them the same way you learned to average them when you were in grade 3. Every vertical slice, you take the halfway point between the two. If you're doing two curves, you take the halfway point between them, and that is provably the correct thing to do. And in ROC space, they've struggled for years to try and figure out how to average ROC curves. And to be honest, the correct answer is convert the ROC curves to cost curves, do the averaging in cost curve space, and then translate the average back, and you get weird looking things, by the way. We've done it. So confidence intervals are important because a cost curve, like there's a cost curve represents kind of an expected value. So for each deployment situation you might be in, what is your expected value of normalized expected cost? Well, it's expected cost, it's expected value. So, but you know, what is the range of fluctuation that you might expect around that? You're not always going to get the average. Are you going to have a tight variance or a loose variance? And so Chris Drummond and I developed an empirical bootstrapping approach to computing confidence intervals around these things, where you would take the confusion matrix and resample it a whole bunch of times, and that gets you minor variations, a whole bunch of minor variations on the cost curve. Like the green cost curve is if you use the whole confusion matrix, and then these black ones are if you do this resampling technique, you get slightly different cost curves, and then you can compute something like a 90% or 95% confidence interval just empirically by counting the lines, basically. And that gets you, then you get rid of the sample lines, and that gets you a confidence interval that looks like this. And so now you know that, yeah, it might not be exactly the green line, but you get a sense that with probability 90%, it's not going to be, you know, above or below the red lines. Statistical significance is done in a very similar way. So the idea behind statistical significance, for those of you that aren't familiar with the idea, is suppose there's a difference between two classifiers. You know, they cross, and so one of them is a bit higher than the other one. Statistical significance is asking the question, is that difference just due to the fact that we have a finite sample, and if we were to actually draw a different finite sample, we might find their order reversed, or they might actually end up being the same. And so statistical significance is asking the question, are differences that we observe statistically significant? In other words, they're not due to the roll of a dice or something, but they actually are genuine differences between the two classifiers. So that's what statistical significance is trying to measure. And the way that we're going to measure statistical significance is by taking the two classifiers and subtracting their cost curves, and then asking, is 0 inside or outside? And then we build a confidence interval around the difference, and we ask if 0 is inside or outside the confidence interval. If 0 is outside the confidence interval, then we conclude with high probability that the difference between them is significant. If 0 is inside the confidence interval, then the old famous statistical saying, we can't reject the null hypothesis. How many negatives are there in that sentence? I don't know, but you've all heard it before. We can't reject the null hypothesis, and so we have to assume that there is no difference between the classifiers, even though it looks like there's one. And so this uses a similar bootstrapping approach, just slightly more complicated. So just to give you a little example of this, there's our two classifiers there, the black one and the blue one. We take their difference. It's this red dotted line here. You notice there's a 0 line, and it goes down into the negative zone there because the difference, I guess what we took was black minus blue. So it's positive over here on the left end, but it's negative over there on the right-hand end. And now we do the resampling, the bootstrap resampling technique on the red dotted line. It looks something like this. And then just getting rid of the sample lines. This is what the confidence interval looks like that will tell us about statistical significance. And when I first saw this, all these pictures are drawn by a tool we have. When I first saw this, I actually almost fell off my chair, because all the times I'd ever heard anybody talk about statistical significance, it was always posed as an is question. Is this difference statistically significant? And just like I said at the beginning of the talk, an is question is virtually never the right way to phrase the question. It's not the right question at all, because if you look at this, it is not a question of the blue one is or is not statistically significantly better or worse than the other one. It's when is the difference statistically significant? We're back to that when question. And so you can see that if P plus is less than 0.3, then 0 is outside this confidence interval, and therefore the difference is significant. And you can look at the over there at the other end. I can't quite read it from here, but something like if probability cost function is greater than, yeah, this isn't P plus anymore, this is PC, is greater than, let's say 0.75, then there's a significant difference between them. But anywhere in between there, like even here, 0 is inside the confidence interval, right? Right here, 0 is inside the confidence interval, so that difference is not statistically significant according to the way we're measuring statistical significance. And so it really is a when question, not an is question. Even statistical significance. Okay, so that's the take-home messages that I have for you. These are the really important take-home questions. The test data that you use is not the same as the deployment situation, and it's almost certainly true that no two deployment situations are the same either. There was an article just about a week and a half ago in a medical journal which said they trained on data from one hospital and they did the kind of usual evaluation of their classifier. They thought it was great, and then they moved it to a different hospital and the performance dropped vastly. And it's for reasons like I've been talking about today. Two different deployment situations, two different performances by the same classifier. And so in your test data, won't represent both of them simultaneously. So that's one take-home message. The next one is the one I just emphasized. Always make sure you're asking when questions, by which I mean under what conditions questions, as opposed to is questions, black and white, yes or no questions. Numerical performance measures don't tell the whole story. ROC curves do maintain the two variables separately, but they don't do a good job of answering some of the important questions that we want to answer. So I guess that's the last bullet point, that cost curves have important advantages over ROC curves. So those are the big take-home messages, and now I'd be happy to take questions. Thank you.
Thanks, Rob. So in machine learning, we usually assume that the test data and the deployment data are the same. Otherwise, a lot of things go away. So I was wondering, but then in practice, that's true, that often the deployment, but many things can go wrong, like the distribution of the clusters that your positives or negatives are in are different, or features are noisy in different ways, and so on. How did this, how were you motivated? Was it in medical applications, or that you came up to this assumption that, okay, let's look at the positive distribution, this is the rate of the positives, that could be different. Again, at the end you mentioned medical domain. Well,
right, so there's actually two parts to that. One was a question, one was a statement, which is true that these two factors that I mentioned are not the only two that one ideally would take into account in evaluating a classifier for a real application. I could comment on that, but the second question is, what motivated me? And to be honest, this work was initially done in the year 2000, and so I'm a bit foggy on exactly what the motivating example was. I had at the time, in about 1995, been working with a satellite company on detecting oil spills in satellite images, and that piece of work. It's funny how you don't actually have to do a whole lot of real-world applications before you get slapped in the face with a whole bunch of issues that, as an academic, you've never thought about, and even as the editor-in-chief of a machine learning journal, you've never even seen a paper about. And so it's funny, that paper gets cited a lot. We published a journal paper on the oil spill stuff, and everybody cites it for the imbalanced classes aspect of it. But I identified in that paper about 6 different issues that we had faced in that one application that have still not been picked up by the academic community. Okay, so there's like a whole industry writing papers about imbalanced classes. I don't even know how you could write so many papers. But it would be interesting, I haven't done it, to see how many of them actually use cost curves to evaluate. I bet you none of them. So they've sort of missed the boat, is they've latched onto the machine learning issue, but they haven't latched onto the evaluation issue. So that's why I wanted to give this talk today. This work is reasonably old, but I think it's really important to keep getting a message out there that how we evaluate classifiers in these things. So it could well be that the oil spill application was one that got me thinking about the ROC curves for sure. Whatever the work was I did with Chris Drummond, I actually don't remember But it was imbalanced for sure. And we thought that ROC curves would be the answer, but they really didn't work for us. So the underlying assumption here, aside from the fact there might be whole things that are missing, is that when you go from, so what do? We start with the confusion matrix, and I said that's the basis for everything that goes on there. And yes, we're going to keep these two numbers apart, and we're going to have our cost curves defined by them. But one of the things that can go wrong, and this is somewhat what you were alluding to, is if you end up in a deployment situation where the true positive rate and the false positive rate of the classifier is actually different, then it all breaks down, right? You have to then go back and say, I actually need a completely new confusion matrix. What this is saying is what to do with the confusion matrix to take those factors into account. But if you find yourself in a situation where those fundamental numbers that we're building everything on top of are not the same in this deployment situation. So that's one of the things that can go wrong. I don't have a clever answer. I don't have a clever answer for that. Part of this talk, especially the early part of the talk, is a warning to anybody out there who thinks that they can just read a paper about some classifier, then gets 99% accuracy, and then take it into their startup company and use it for classifying whatever it classifies. Basically, buyer beware. This thing in your situation may not perform nearly as well as what you read in the papers. So watch out. There's a question here in the front, near the front, yeah.
Nowadays, people are doing things with lots of classes. So is it easy to scale this to 1,000 classes? And it seems like that might be kind of complicated, but like an image classification or some of those things that might have 10,000 classes.
Yeah, so
does it scale well?
The math scales fine, okay, because these are just formulas and you're computing stuff. So the math scales fine, but the possibility of visualizing completely disappears because of the shortcomings of the human ability to visualize beyond. I don't know what I know you told me earlier you're a physicist, so maybe you can do 4D and stuff, but I can't. I have trouble with 3, to be honest. So the dimensionality of that space goes up, or the confusion matrix goes up quadratically with the number of classes. And so even if you have 3 classes, you're up to something like 8 dimensions. Because if you think, every one of those things in my confusion matrix is a separate number that are independent of each other, except they all add up to something. So they're basically all independent, and so the number of dimensions doesn't grow linearly with the number of classes; it grows quadratically with the number of classes. So that's sort of one problem. There are some approaches to this that one could take, and one of them is it's not uncommon, or at least when I was actively working in machine learning, in multi-class situations, to evaluate one versus the rest. So this is now back to being a binary classifier. Think of the letters of the alphabet. Can you distinguish an A from everything else? And then can you distinguish a B from everything else? And can you distinguish a C from everything else? And so there you have a 26-class classifier, but you can do some kind of performance evaluation by turning it into a binary problem. Another thing that if you know that confusing 2 classes is very low cost, then you can treat them like one class. So if you think of cost matrix, for example, if this row and if this column have very similar numbers all the way down, and this row have similar numbers all the way across, then you can just treat them as one. So you can sometimes reduce the number of classes that way, but I'm not pretending that I have a good answer to your question. The fact is that I really like the visual aspect of this, and that's gone. But the math still holds up.
Have you seen Silicon Valley? There's pizza and not pizza.
Hi, so I am a little curious about the whole issue, as you said, test data and leading to not deployment situation. And I think it echoes a little bit the previous question, but how much is that indicative of you actually have changed the actual problem that you're trying to solve once the rates, the false positive and false negative rates are changing. And I guess in the hospital setting, that seems pretty, like you have a set of people, but each hospital that has a different rate of disease is probably treating a different population. So you might want an entirely different classifier for that population as opposed to just based on the rate of what you're dealing with.
There is I'm confusing two things in your question, so I don't know, but I'll come back. I'll just say one thing, and that is, what is the class ratio that you want in the test data? Like, you could ask that question, Even if you knew the deployment ratio was 16:1, would you put 16:1 in the test data? And the answer is no, because the whole point of the test data is to get good estimates of the false positive rate and the true positive rate. And so you should use as much data as you have from each class to get the best estimates you can of those numbers. Because it has nothing to do, the nice thing about using false positive rate and true positive rate, as opposed to a measure that some people use called F1, the F measure that you see in information retrieval, is it actually mixes across the rows and across the two rows. It has one number that it takes from the first column, and it has another number it takes from the top row. And when you do that, then the ratio between the two rows actually really makes a big difference to what you get out of the test data. But the way this is being done for ROC curves and for us is the ratio between the two rows does not come into the equation. You've got, everything in the top row is based on the top row, and everything in the bottom row is based in the bottom row. And so you can change the ratio of top row to bottom row any way you like, and it doesn't affect anything. So you should use all the data you have, no matter how it pertains to the test data. But then the second part of your question was just really kind of going back to what he said is, if really the underlying numbers are different, and this is where the cost curves are only half the solution. They solve the problem if, like in the hospital situation, I honestly don't know. Was it a problem that the classifier's actual true positive rate was wrong, or was different, or was it just that there was a different P+, right? And it could well be, and I think often it's just a different, almost you said this, is that, in this hospital they get lots of people with a particular illness, and in the other hospital they get very few people with that illness. That's a change in P+. That's not necessarily, that's not the classifier having a better or worse true positive rate or a different true positive rate. And so the two things are distinct, and I think that at least to some extent you can deal with transferring the classifier from one situation to another using the cost curve analysis and saying, in this hospital we should use the red classifier, in that hospital we should use the blue classifier. There's a question over here.
So it's interesting that you've put the empirical probabilities into the x-axis, as you say, that becomes an independent variable. But then you've fixed your costs. So is there an argument saying that the variability in the empirical distribution is harder to estimate, and that you're more certain of the costs? Why wouldn't you treat the costs as uncertain as well?
When you say I fixed the cost, were you referring to that y equals something x formula?
Yeah, you had a cost for the two types of failures, and they appear as
Oh, yeah, no,
constants.
those are variables. Those are variables. Yeah, sorry, maybe I glanced over that too quickly. They only show up clearly in this one slide here. Yeah, these are not constants. These are unknowns. This is an unknown, right? We talked about that being an unknown. In the deployment situation, what is P+? I don't know. In the deployment situation,
It was uncertain.
it's not only uncertain,
Okay.
we're
So-
treating it as a complete unknown.
So
And so this whole thing is a whole bunch of unknowns that are being multiplied by each other, okay? And so, yes, there's nothing in this formula except the constant 1 that's known. Everything else is a complete unknown. This is just a formula. If you were in a specific situation and you could measure all of these numbers, then that would tell you exactly where you were on the x-axis.
I'm with you.
Okay?
So there's actually multiple different scenarios that could correspond to any given value.
Absolutely. In fact, the miracle here, and I didn't answer this part of your question because I have never worked it through fully, is it's sort of a miracle that we have 3 unknowns and we managed to squeeze them all into a single x-axis here. The natural way to think of this is you've got p plus and c minus plus is a separate dimension, and the other one is a separate dimension. Like this looks like it should be a 4-dimensional already, with the performance then as the 4th dimension. But it turns out it's a linear manifold in that 4-dimensional space, and so you can just do it as 1 dimension x, and then the y is the other dimension. So it's kind of a miracle, and I don't know what happens when you scale up the number of classes, whether it stays, I doubt it stays a single dimension anymore. I think you'll end up having, if it did, then we would be able to visualize it in 2D, but I don't think it does. So, but yeah, these are all unknowns. And so what it does, when I said that when you look at the crossover point, that gives you a hypothesis you have to test, are you to the left of a line or the right of the line. When you are now using this full-blown version of it, you have to test the hypothesis, is this x less than 0.7 or bigger than 0.7? And that's obviously a much more complicated thing to test because you have to, this is a real mishmash of a whole bunch of different stuff in a funny way. So you have to test the hypothesis, is this x less than 0.7, if that's where the crossing point was. So it's a more difficult hypothesis to test.
Let's first thank the speaker again.
Yeah. And I want to thank all you for coming out on a smoky day.